I'm Mayla Boguslav, and I research researchers. As a researcher, I get this incredible opportunity to advance science and knowledge, and I do not take that lightly. Taxpayers like you fund research, so we owe it to you and ourselves to ensure you can access and understand our new knowledge and findings. Welcome to the Ignorance Podcast, where we learn about current questions in research. I live by the motto, ignorance is bliss, because when you don't know something, it's an opportunity to learn. Let's welcome our guest researcher for today. Please introduce yourself by name only and your favorite thing to do outside of work.
Hi, everyone. My name is Melissa Haendel, and my favorite thing is I love to cook.
Anything specific that you like to cook?
I like to cook a lot of different international cultural foods, and I love to make fancy dinners, and I also make wedding cakes.
Ooh, yeah. Now I know what house I should go to for all of these things if I want some really good food. What questions excite you in your work? What questions are you currently pursuing?
So one of the things that drives me is our inability to really understand the natural history of patients with rare diseases, how we define rare diseases, how we diagnose patients with rare diseases, and our ability to sort of characterize rare diseases such that we can actually identify treatments and hopefully have better outcomes for those patients. And there's a lot of different moving parts that have to come together in order to make those dreams come true. So that's one of the main initiatives that I have right now.
So I guess what's the question? Is the question, how do we better diagnose and characterize rare disease patients for better treatments?
Well, I think for my research, one of the challenges that I have is that a lot of my research is actually not really research. It's really about building infrastructure, implementing technologies to help facilitate others doing research, right? So we can't really research molecular mechanisms of rare diseases to identify treatments if we don't actually know which patients have those rare diseases. So building infrastructure to document those rare disease patients in electronic health record. My team does do research on methods on how to build a better strategy around diagnostics using different types of methods and comparing different kinds of methods, but mostly our research focuses on implementation science and kind of more infrastructure focus. So I do think there's an important question in all of that, though. I have a fundamental belief that all people are an N of one disease or healthy state. And when we define diseases, they are groups of people that have commonalities, and they're potentially useful groupings for care decisions or outcome prediction. And, the question is, what are the meaningful groupings of patients? And so how can we better characterize individual patients such that we can have those meaningful groupings? So, for example, my lab works on a rare disease that's not too rare called Ehlers-Danlos syndrome, which currently the hypermobile type does not have a known molecular mechanism. So we're using a combination of approaches using electronic health record data to stratify those patients into different categories that where their symptoms, the features that they might have as documented in electronic health record might differ in those different subgroups, with the idea that maybe then those different subgroups correspond to different molecular mechanisms that we can then reveal with laboratory kinds of studies using patient-derived samples where we can actually look to try to reveal those molecular mechanisms. And then if we can do that, then we've basically defined new subtypes of Ehlers-Danlos that we can then develop therapies against. But until we actually narrow down what those are, that's a really hard thing to do.
Yeah, I think people forget that you need to actually be able to identify and name the thing that's going on before you can really get at treatments. And that can involve actually characterizing different versions of what thing may be going on, as you're saying in that example of EDS. Can you give a little bit of a definition of what this syndrome is, just for people to know?
Yeah, so for anyone who's read The Fourth Wing, it's a fantasy novel. It's the story of a woman who goes to dragon battle school, and she has hypermobile EDS. It's a disease that afflicts more women than men. It tends to affect adolescents and young women when it's first onset, although it has lifelong symptoms. And it's characterized by hyper flexibility, very elastic skin and easy bruising, and very sort of easily dislocated joints. So a lot of connective tissue weakness. And it's influenced by hormonal changes during menstruation or during pregnancy. And it's also known to have some environmental factors. So diet and exercise can also change the perceived sort of severity. But we don't know the molecular mechanisms, although some genetic variants have been found in association. They're not causal. So it's probably a combination of specific genetic characteristics and environmental characteristics that are together causal for the disease. But that's what we're trying to figure out. What are those specific subtypes?
How many people are affected by it, and what defines a rare disease?
Oh, well, that's a hard one. Different countries define what is a rare disease differently. I believe in the United States, it's 1 in 200,000 or less in terms of prevalence. But the prevalence of rare diseases is very hard to determine because most rare diseases don't have a diagnosis code. And so you can't just go query all the electronic health records to find patients that have, many rare diseases. Now, hypermobile EDS does have a code, so you can code for them. But when we actually look for phenotypically similar patients to patients that do have a rare disease code for hypermobile EDS, we find there's a lot of patients that haven't yet been diagnosed with that code in the EHR. So what's the real prevalence? Is it the prevalence of patients that have the diagnosis, or is it the patients that look like people that should have a diagnosis, right? And then it gets harder and harder when you have patients, you have rare diseases that don't have a diagnosis code. So we have a very poor understanding. We did a study several years ago where we looked at prevalence of 14 different rare diseases, mostly because we were characterizing their care trajectory and the cost of that care trajectory in the different health systems. And these were all 14 rare diseases with ICD codes. The prevalence was just very different in these different healthcare systems and very different from what's reported in the literature. So we don't have a very good handle on the prevalence of most rare diseases. There's been estimates, but I've never been able to find an actual authoritative citation for approximately 1 in 10 people have some kind of rare disease. Now, it's not to say that every rare disease is life-threatening or necessarily detrimental to your health. That's collectively quite common, right? It's like at the level of like being colorblind. So, but we're doing a very poor job of documenting them. And in fact, we in our group have now identified over 15,000 different known rare diseases.
Wow. Yeah, I know I kept asking you questions that may be harder and harder to answer, but just to showcase the complexity of all of this, and if you really can't even name it or identify it, you're screwed, right? You really can't do anything, which is exactly what you're saying. And then you can't really answer such basic questions of what is the prevalence of this disease because you don't have a code or, other factors that are there. People don't know how to diagnose it. People aren't getting diagnosed for it. So with all of that, how do you hope to impact the world?
So partly because our diagnostic work was negatively impacted by the fact that none of the sources of information about rare diseases actually agree with one another, especially computationally. And so it became like this giant spaghetti ball of like everybody, cross-referencing everybody else, and all the knowledge was inconsistent. And so if we can't bring it all together computationally, it makes it such that the ability for the diagnostic tools, these bioinformatics pipelines, to actually diagnose patients in the same way in different countries with using different knowledge sources becomes a rather intractable challenge, right? So not everyone is an expert in every rare disease. They can't be, right? Even so, we need to make the knowledge more consistent and more discoverable. so that diagnostic tools, information resources, and even clinical textbooks and clinical, knowledge sources can really take advantage of that shared initiative. And so we created over the past 5 years or so an initiative called the Mondo Ontology, which is a kind of consensus resource that aims to coordinate across all these different individual rare disease knowledge sources, recognizing that many of them have expert clinicians and wonderful content and wonderful communities around them, but just aiming to provide kind of a framework that connects them all and organizes them all so that there can be a computational representation. And so those Mondo codes now are sort of the handle by which you can then access the world's different sources of knowledge about any given rare disease in a more consistent and comprehensive way. And so it really aids communication across countries, across context, across medical disciplinary areas, and also helping to support moving patients along in primary care. And recently we've been able to work with a company called IMO Health, which is one of the terminology service providers for electronic health record systems and other clinical systems, including Epic. And they have integrated Mondo now into services that are now provided to Epic. And we are very excited that our Mondo terminology, that was really community developed. We had 100 authors on the paper, 5 years of community effort, now are going live into electronic health record systems in the United States. So hopefully that'll happen around the world. But for right now, we're just kind of excited that for the first time, we'll be able to actually track the rare disease codes that don't exist currently in electronic health record systems, so we can start documenting those individuals.
Yeah, that's an amazing impact. In the team science world, we constantly talk about this issue of shared language, that you really need to make sure you're all speaking the same language to talk to each other across disciplines, especially as you mentioned. In now being more in the team science phase, I've realized a lot of my work has actually touched on that. A lot of this ontology work, a lot of the terminology work is really trying to do a similar thing, that if you don't have a shared language across all the people, you really don't know what you're talking about together and can't really do anything. And so that's huge. Congratulations on getting it into electronic health records. That's amazing. And I didn't realize there was a terminology piece to it. Like, it makes total sense that there's one group or maybe a few groups that maintain all the terminologies that go into electronic health records. And it's amazing how many people you have to work with to be able to get all these things to happen in general.
Yeah, and our next effort is really going to be to try to work with insurance companies and congressional representatives to try to create some new policies around how we actually code for rare disease patients in electronic health record systems so that we can better monitor care outcomes and understand prevalence. And then also for research purposes, really be able to support more mechanistic research by having access to data that's actually coded properly, so that, similar to what we're doing with hypermobile EDS, we can now do that much more easily for other diseases that don't currently have a diagnosis code.
Yeah, that's amazing. And obviously will hopefully help so many people. Who has influenced you? Who are people you look up to?
That's a wonderful question. Well, I just had the honor of celebrating a really important award for my dear colleague, Chris Shute at Johns Hopkins. He won an award from the American Medical Informatics Association for a Lifetime Achievement Award. And he has been sort of a scholarly father to me over the years. There's not that many people who work in the ontology and terminology space that really kind of think about interoperability, and especially interoperability between clinical care and clinical data and basic research data. And he's really helped me kind of grow my understanding of clinical informatics and electronic health record data, and how can we kind of create that interoperability across what he calls the chasm of semantic despair. And so I've always loved that term since the first time I heard him say that. And so I've spent a good chunk of my career now working in his footsteps, his footprints, trying to cross the chasm of semantic despair and really link mechanistic data to clinical care data. So he's definitely one person that I really greatly look up to.
That's great terminology, chasm of semantic despair. Um, in my head, I think about it as who's really using the terminology, because kind of in the translational space, in the clinical space, there's the chasm of drug development when you have the drug and the basic sciences, but then need to actually get it out into the world and see how that works and the commercialization piece of that. And to me, language is such a fascinating way to think about that too, where, if you don't have the same language across the different spaces, then you can't really do anything. So I would argue you've already started doing that by getting it into electronic health records. So that way it can be used in both spaces. And it sounds like you're going to keep pushing that to get it into policies and insurance companies, which feel like really daunting and hard problems to solve. So that's great terminology, and congrats on the award for him, and exciting that you got to celebrate it. How do you know if you've been successful at your work and as a researcher? What is your evaluation criteria?
Well, that's a good question. I'm like the quintessential middle author. Like, I'm never going to have a first author or last author science or nature paper where I've discovered some big new discovery. That's just not the kind of work that I do. I really want to enable others to do that kind of exciting discovery research. My prior dean asked me, so what is it that you actually work on? And I said, look, carburetors have been historically a critical component of an automobile. But when you look at a race, like a race car race, you think about the paint on the car, the sleek design, the sexiness of the driver, their outfit, and then they win the race. And you don't really think about all the people, the small army of people who built all the parts of that car, the pit stop people and the people who built the carburetor. So I told my dean, I'm the person that builds carburetors for other people's race cars. And, you've got to have that infrastructure in other fields besides biomedicine and science, like physics and engineering. They spend a lot more money and time and teach more people to build infrastructure to help support that discovery science. We don't really do that so much in biomedicine. And so we really, we really need that kind of infrastructure, but it's very unsexy. And so how do you know you've been successful is probably a different set of criteria for someone like me than it is for, somebody who's doing hypothesis driven research. I think in that context, it's use. Do people use what you built? Mondo is a great example. People are using it. It's going into healthcare. It's being used by other large programs. I was at a knowledge graph meeting recently, and out of like 20 plus talks, there wasn't a single talk that wasn't using some of our resources. I think another measure is whether or not something's been discovered or implemented using that. So patients are getting diagnosed using our resources. That's a critical outcome. Sometimes those kinds of outcomes are very hard to track, though, especially because a lot of our work is very open source. We don't know who's actually using it or how they're using it, especially if it's a commercial company. And I have a wonderful story actually from Mondo where a dear colleague of mine had a rare disease son, and he used Mondo to help reveal the infectious agent that his son had an infection and was able to treat him. And so he says Mondo saved his kid's life. I think those kinds of stories are few and far between, but when they come about, you can really see the way in which people are actually utilizing things and the impact it can have on someone's life.
Yeah, this is one of my favorite questions because I don't think it's super easy to answer. And I agree with you that it's not necessarily easy to track. This is some of the work that I'm trying to figure out in my career, is how do we really understand impact and how do we track impact? And really also just thinking about pipelines to impact. How do we actually get to that impact too? And so I love all of those, right? Whether it's the stories, whether it's the usability, the fact that you go to a conference and there's lots of people to explain the authorship piece. Researchers, when they publish, the authorship order can matter. And so usually first author means the person who wrote it and they get the most credit. Last author is usually a mentor. And then middle authors are kind of people in the middle. And so you don't necessarily get as much credit. So it's kind of similar to that carburetor idea that you're really on that team that helps with the pit stops versus front and center with everything that's going on. And I really relate to what you're saying about infrastructure too, because I also work for an infrastructure institute. And so it can be really hard to get people on board with some of these ideas because they don't see the value. And I think that's the other piece that I'm trying to work on is how do we showcase the value of some of these things that feel not valuable, that tend to fall off the wayside pretty quickly. And usually it's because you can't really run the counterfactual, right? You can't always know exactly what would happen if you didn't have it. At least in my case with team science stuff. But in this case, it seems like you're really laying the groundwork to be able to showcase both. That here's what we were able to do before, and now here's all that we can do afterward, which is really great to see. So I love those evaluation criteria.
I think another related story that's more in the kind of translational science arena that I know you're interested in is, when we were in the pandemic, Dr. Shute and myself co-founded the National the National COVID Cohort Collaborative, or N3C. And in that context, we got over 200 institutions to share clinical data together and, made that data available to researchers in a secure environment. And it really changed the way that clinical informatics works from being a very institution or project specific kind of set of activities, mostly because of data sharing constraints, to being one that could be really, scalable and collaborative. One of the things that really made the big difference that, as they say, never waste a good pandemic. Was this idea that we had these different levels of attribution for the manuscripts that would come out, and we put into place a process that said, hey, if you created a method or an algorithm or a code set or an artifact, a computable phenotype, and then somebody else used it, then you would be requested to see if you met authorship criteria and you could be an author in the paper. And so we went from, individuals just sort of generally not wanting to share their code or their research until it's published, right? To actually wanting to share it as quickly as possible so that it could get better and get used in the next publication, and they might be an author on that publication. And so we ended up creating this 3-tier system where we had masthead authors, which would have their names on the paper, and then we had a consortial author, which are still authors and are still indexed in Medline. So that would be the list of all the sort of, contributors that still met authorship criteria. And then we also had acknowledgements. And so for every single paper, it would go through this review process where the publication committee would look at what were the artifacts that were used and email everyone who was in that given team that was related to whatever those artifacts might have been. And they would fill out a form saying what their contributions had been to that paper. And then it would automatically generate the author list and all the acknowledgements for the paper when the paper was submitted. When we submitted the first paper for N3C, there were 199 authors on it in Jamia. It took them over a year to index them all because no one has ever written a paper with 199 authors on it in clinical informatics. So I think we basically, as a community, really transformed clinical informatics into something that's much more akin to those large genomic projects, that, really sort of took a village, and really changed how people think about the way in which they share their work and build on each other's work. And so I think it is changing, and we need more resources and infrastructure that can allow that to happen, and more commitment to providing, attribution like that when we build on each other's work like that.
Yeah, that's great because I think a lot of what we talk about in teen science with authorship stuff, or just in general with academia, is that the incentives don't match the goal. And so you've created a really nice incentive system that if you share everything with us, we'll give you credit and you'll be able to be a part of this much more compared to, how right now we really get promoted in academia individually. And that incentive really drives how people work and that they really want to make sure that they're getting what they need to be able to get promoted. And so I really like that example as a way to change the system. And also, the amount of infrastructure you put in place to make that all happen is huge. And so you're really practicing what you preach in all of those different ways, which I really appreciate about you for sure.
Yeah, it's really fun to see too people from expert clinicians like with so many exciting questions to ask, and people who are data scientists able to ask them in real time, and just everybody kind of working together across disciplinary boundaries to sort of generate answers. And that was a special time in science.
Mhm. Yeah. What has been your most surprising result?
I can speak to two different results. I think it was in 2013. We wrote a paper where we evaluated the reproducibility of science based upon whether or not we could determine what the ingredients in the papers were. So, do we know which mouse it was? Do we know which cell line it was? Do we know which antibody it was? Do we know which peptide it was? And we were very surprised that less than 50% overall were actually reproducible. Not because of anything having to do with the methods, which are even a different level of challenge, right? But like, we didn't even know what the ingredients were. So, somebody will just say, oh, the Hox mouse. So like, well, which Hox gene, which Hox mouse, which genotype, right? Like, you wouldn't know which one they were talking about. And the fact that that could just get published like that without anybody having any kind of oversight over that, I think that was really surprising. And Francis Collins wrote a commentary in The Economist and cited our paper, and it changed NIH policy for reproducibility. So it was very impactful and a very surprising result. I mean, everybody was kind of starting to wonder how reproducible is science in general, but I hadn't realized it was that bad just because of the lack of specificity. It would be like reading a recipe book where you just say, add spice, and not which one or how much, right? Yeah. So that was one story. Another story is even earlier in my career, and I think this also is a little bit related to reproducibility, but when I was in graduate school, I had discovered a gene and knocked it out at the same time using early gene trapping methods. And I got to name the gene. I named it axatrophin because it caused neural degeneration. And what was really surprising is that when I put that mutation on a different mouse background, the mice didn't die like they did on the first background. They actually lived. And so in the mice that on the background where they died, the neurons did not cross the midline in the brain. And in the adults that lived on a different background, they had neural degeneration of sensory neurons. And so I was very surprised at how different the phenotypes were on these two different mouse backgrounds. Of course, now we have lots of examples of that since then, and there's a lot more careful mouse genotyping happening as well. But also surprising is to this day, the gene has been renamed. It got renamed at one point to March 7, and then it had to get renamed again because March 7 would be a date in Excel. And so it would always change the name of the gene. So they renamed the gene again. So that was kind of a funny thing. And so also speaking to reproducibility and provenance of that knowledge and that information, if you look at the literature, different time points that would be named axatrophin or March 7 or several other names. And to this day, we still don't really know that much about what it does. That gene at the time basically was so toxic to every cell I put it in, it was very hard to study. So here we have this gene that we've known about some aspects of its function that was back in the late 90s. We still don't really know very much about what it actually does. It's expressed in almost every tissue type. So there's still like just this incredible unknown. And so several surprising things in that story. But still some scientific mysteries.
So many fun themes. This idea of language matters, both writing down what you actually did and ensuring the specificity of it, and then also the changing of names of genes. That all of that changes over time and there's reasons, and you can lose the provenance as you're saying, and it really matters what those were. Also very cool that you got to name a gene, and also that you were quoted by Francis Collin and The Economist. So yeah, surprises really help us do more research. And so I can see in your career how that's really impacted the research that's been happening. And there's still a lot of questions to ask and mysteries to solve. Yeah, so what is your favorite disagreement?
I might have several. I think one of them is this question about open source development versus commercial development. And earlier in my career, I'm a huge open source, open science enthusiast, especially in the rare disease space, because if we don't share, we don't know, right? It's really critical when information is sparse to share. And rare disease patients themselves will post everything on Facebook sometimes because they know that if they share, they'll find others like them. They can help somebody else, right? But as I've gotten more mature in my career, I've also started to recognize that we can't keep everything open source and still be successful at helping the very people that we aim to help. So by having commercial partners, like IMO, for example, with Mondo, I could never get Mondo into healthcare by myself. It takes those kinds of partnerships and those implementation pathways to be able to actually get things into care so that they're actually used by real people in the real world and really affect outcomes. And, there's a lot of work that people don't recognize that commercial partners can do. So all the regulatory work, all the security work, infrastructure, all of the sort of business development that has to happen in order to actually implement something into care, or into the real world in whatever context. It takes a different kind of creativity and innovation and persistence in the business sense that isn't something that we're very accustomed to or trained to do in basic research open science community. But there's a lot of disagreements about this, right? I have many colleagues that think, oh, I'm going to save the world by just making everything open. And I agree with the sentiment. We, have requirements in our lab to make our code open, but there's also got to be this balance for ensuring that things get implemented. And also with the change in funding climate that we're experiencing right now, there's an opportunity to kind of tilt that balance a bit more towards the commercial side of things, where we can actually have some more sustainable revenue that can support the open science part, right? So if you just hold a little bit back of your IP and work together with some commercial companies for implementation, you could help more people. And you could provide some sustainable revenue for your open science initiatives as well. And I think this has been a huge tension in the open source community for a long time. Commercial companies are viewed quite negatively by the open source academic community. And a lot of times the commercial companies don't want to use the academic work because it's got so many constraints on it for a variety of reasons. And so there's this tension and argument there. I think that this current funding climate is going to actually tilt that a little bit more towards commercial partnerships. And I think also the pandemic did that as well. We had to partner because we got the people and the technologies that we have, and we gotta work together to save people's lives. And some really great academic public-private partnerships came about during the pandemic in all kinds of contexts. So I think that's probably the biggest disagreement that I'm passionate about bridging.
Yeah, for sure in grad school, like open source was really valued. And I've never actually thought about it in that way. I've been thinking about a lot recently, resources that can really help be those pipelines to impact at the end of the day outside of the university. One big one that exists on most campuses are tech transfer offices, right? That really are supposed to help with a lot of this work of creating those public-private partnerships. And you're right, we can't do a lot of these things without some of those other partnerships. And that does come with their own constraints, just as everything does. So thank you for saying that, because I definitely just learned something about the importance of both, not just one or the other. Okay, if you could do anything not limited by grants or other factors in your space, what would you be doing? What is your vision for the world?
I really want to realize a more real precision medicine strategy for humanity. And that might be very lofty sounding, and it is. But I have some ideas about what that could look like. Historically, our clinical encounters were documented in paper files, and in fact still are. I was just at my kid's pediatrician and they still have paper files. So even though we have a requirement for being, quote, electronic, there must be something they enter stuff into. I don't know, but they're not using it in the day to day. The electronic health record systems that we have are kind of more like electronic versions of the paper record than they are a health portal. And they're also not a precision health portal. They are a health encounter disease tracking portal. So I have this philosophy of putting the patient back together again, with essentially this idea that there's data about us individually all over the place. We have our wearables, there's my Aura Ring, we have our environmental and social variables. We have data that's captured in the context of healthcare or other contexts, like maybe I did genomic testing or did a genealogy study. So the idea that the health record system of the future would be a precision health portal where we characterize patients as people and as biological subjects, where we can document our own experiences with our health, where our systems that we have that track us, our wearables, and even like things like educational outcomes are incredibly important outcomes. In Europe, you can track those as health outcomes for kids that might have developmental disorders. We can't do that so easily in the United States, for example. So I have this dream that the health system of the future will be more of a health portal, and it's both for patients and for caregivers and family members, that that everybody works to make that system useful for all the different stakeholders. Because right now, it's mostly useful for billing and for clinicians to keep track of the care that they provide. It's not really about your health, and it doesn't really access most of the data about you that actually influences your health. It doesn't tell you anything about your environment or your social determinants. It doesn't say anything about your diet. It doesn't say anything about most of the biological attributes of an individual. And so my dream for the future is that would be a platform that the patient would be in charge of rather than the health system. And the patient could then provide access to whomever they want, their family members, their doctors, research studies. And it's all connected. The patient's put back together again.
I love that dream. I am excited to follow your career to see that come true. Because in grad school, I heard a wonderful talk by dean of a medical school at the time about exactly what you said, that we had an opportunity to really completely change how health worked, and we just replicated it. And not only replicated it, but you can't do the same things that you can do in a paper record as you can do online. So for example, he was saying that the reason there's a lot of copy over between different records in electronic health records at this point is because, at least in the paper record, you could see multiples at the same time. But that was actually really difficult in the electronic side because you couldn't have different tabs open, even though you could have different pages open in the physical record. And so that meant people just went to one spot, copied it, moved it to where they were, and then just left it. And so much copy and paste and these other problems emerged because we didn't really rethink it fully. And so I completely agree. I've never heard a good version of what it should be. So thank you for giving me a really awesome version. And I'm excited to see it come to fruition in that way. So last question, what has changed in your life because of your research? What do you pay attention to more because of it?
I think about research differently. I had a lot of challenging things happened to me in my career. There was data fabrication in one of my labs. I had a abusive supervisor. I had a supervisor who refused to acknowledge that the research was all an artifact. And because of all those things, I've ended up working on reproducibility, and I used to teach ethics. And I think it's really led me to change also how I run our group. My lab is not called the Haendel lab. It's called the Translational and Integrative Sciences lab. I don't really know very many people that don't have their lab named after them. It's not my lab, it's our lab. And we have multiple faculty in the lab that run their own programs. We have a shared love of semantics and interoperability, but people come from all different backgrounds. And so we're a little bit of a motley crew. I have a veterinarian, there's an MD, there's been librarians, cell biologists, computer scientists, an oceanographer, and the list goes on. People come from really different backgrounds. And that sort of diversity of thinking and backgrounds and perspectives can be challenging sometimes, no doubt, but it can also really enrich the way we think about things. And I think that works really well for a team that focuses more on building infrastructure than doing hypothesis-driven science. And more recently, I think we've gotten much better, especially since we've moved to University of North Carolina, where we have access to more trainees. It's a great environment for trainees too, because they get to take advantage of the infrastructure to actually do hypothesis-driven research, like the hypermobile EDS work that I mentioned. People just work on different things that sort of apply those semantic infrastructures and interoperability to do more hypothesis kinds of research in their training context. So that's another good measure of whether or not our science is working, is can our trainees use it to do actual science. I think that those challenges in my earlier career have really changed my focus and how I think about the act of actually doing science.
Yeah. That's amazing. A lot of people give the evaluation criteria of students as a big one, because a lot of professors teach in general. And so that's one big evaluation criteria, that you're training the next generation. But the other piece that you really said there is creating actual data sets for the researchers, for the trainees coming up. And I think that's such a critical moment. I heard a talk about the importance of data sets and how so many trainees were able to do their research because of access to data sets. And I'm one of them. Because PubMed Central Open Access existed, I was able to do a lot of my work and not have to worry about getting access to things and going through all these hoops. So thank you for continuing that process and helping people be able to do that in general. And with that, I'll let you introduce yourself with your name again and your job title and your field and anything else you'd like to share.
All right, thanks. Well, this is Melissa Haendel. My job title is I'm the Director of Precision Health and Translational Informatics at the University of North Carolina at Chapel Hill in the Department of Genetics. And I think, it's really great that you're doing this podcast. I think more scientists of all flavors need to focus a bit more on scientific communication and sharing the stories. And so not only are you sharing my story, but you're helping others to learn to share their own stories. And so I really appreciate that you have this podcast.
My biggest takeaway is that Melissa wants to ensure people use what she builds. There's always a place for theory and thought experiments, and I think translating even those into use can be beneficial. I hope my podcast is used to help society better understand research. You can help me with that by sharing the podcast with one other person. What is one use for your work? This podcast is hosted by me, Mayla Boguslav, and produced and edited by Joshua Mendel. To learn more about this episode's guest and any cited or named people, take a look at the episode description. Thank you for listening to this episode of the Ignorance Podcast. Please follow the Ignorance Podcast wherever you get your podcasts to learn about science through research questions.